Okay, so thanks very much to the organizers for the invitation to talk at this great conference in this great university. So I'm going to discuss work done in collaboration with my really good collaborator, Takahiro Nishinaka from YITP in Kyoto. This is based on work that we put out a little earlier and a bunch of other things that we've been thinking about for the last couple of years. And also, I'll sort of cryptically allude to some work in progress as this talk goes along. Okay, so the claim of this talk is somewhat technical and seemingly narrow. So before I get there, I'd like to explain a little bit better the broader setting, as well as some open questions that might be of broader interest that this talk will touch upon. So in this talk, I'm going to primarily focus on, well, exclusively focus on theories with 4-dimensional n equals to 2 superconformal symmetry. I'm often going to discuss closely related 2-dimensional chiral algebras. And I'm going to focus mostly on theories with exactly marginal deformations, in other words, conformal manifolds of these theories. But along the way, we'll present some results about isolated theories as well. So what are the open questions that we're going to touch upon? So the first one is the question of, if you have an n equals 2 conformal manifold, is it true that there are always cusps at which free gauge fields emerge? So answering this question would be some kind of landmark along the way of trying to classify field theoretically the space of n equals to 2 superconformal field theories. A closely related question is, if you have an n equals to 4 quantum field theory in 4 dimensions, do you necessarily have super Yang-Mills? Another set of questions that this talk will touch upon is whether there are interesting new relations between conformal manifolds and moduli spaces. So these are two natural extended geometrical objects that exist in many of these theories. And so one question one can ask is if there are interesting relations. So we know from ADS-CFT that there are relations between moduli spaces in gravity and conformal manifolds in field theory. And we can ask if there are similar relations just within field theory. So in the class of theories that I'll consider, this will amount to some kind of reformulation of some analytic statements on the conformal manifold, like vanishing of beta functions, in terms of some algebraic and geometric properties of the theory and of the operators that describe the moduli space of the matter theory. So, and finally, the third question is to understand general relations between chiral rings and chiral algebras. Okay? So the upshot will be that we'll get some new bounds on global properties of conformal manifolds from sizes, in quotation marks, I'll explain what that means later, of chiral algebras. And we'll touch upon this and a lot more. Okay? So before I get there, let me just review a little bit some general aspects of n equals to 2 superconformal field theories, conformal manifolds, and then some aspects of chiral algebras. I'll tell you the claim, and then we'll discuss a proof. So n equals to 2 theories have a U1R times SU2R symmetry. And this factorization is a source of a lot of very interesting physics. So the operators that are charged under U1R are the chiral primaries of the theory. So these are operators that are annihilated by all the anti-chiral Poincare supercharges. And they get their dimensions from the U1R quantum numbers. Now, if you start from some n equals to 2 superconformal field theory, and you have some chiral operator, chiral primary of dimension 2, and you have a small deformation, and you add a small deformation of that theory to the action, you necessarily get an exactly marginal deformation. And this space of exactly marginal deformations has a natural metric on it, the Zamolodchikov metric, which can be computed from the 2-point functions of the chiral and anti-chiral primaries. This metric has various nice properties. In a unitary theory, it's Riemannian. And moreover, for this amount of supersymmetry, it turns out to be Kähler-Hodge. So in all known examples, this deformation, delta lambda, is just some deformation of a gauge coupling. So you have some theta angle and some real gauge coupling G. And the operator that you add to perturb the theory is some Casimir of the gauge group. Okay? So all known examples are of this type, where you start with some isolated matter theory, you gauge it, and you get some, in a conformal way, and you get some manifold parameterized by gauge coupling. So one of the simplest examples is SU2 super QCD with NF equals 4. So there you have a gauge field, phi, transforming in the adjoint of the gauge group. And you have matter fields QIA. these matter fields are sort of combined into some holomorphic moment map, which you couple to the gauge field, and then you study the theory as you vary the gauge coupling. So in a more invariant sense, what you do is you perturb the prepotential by this Casimir of the gauge group. So this conformal manifold has been explored by Seiberg and Witten, and it has many interesting features. So I won't describe all of them, but roughly speaking, as you sort of meander along the manifold and you go far out, you find descriptions that are far out in terms of this Zamolodchikov distance with respect to this metric. You find some free field theory. So in particular, you find free gauge fields coupled in this case to free matter. And one general question is this diagram essentially enough to classify all such manifolds? Okay, maybe you need to shrink or enlarge whatever the size of this, the width, maybe you need to increase the number of dimensions, et cetera, and maybe you need to consider more exotic isolated theories at the different cusps. But one basic question is this enough or not? Okay? So, well, we're not going to quite answer that question, but we're going to give some quantitative tools to try to analyze it. Okay, so that's one set of important operators. Those are the elements of the chiral ring. And another important set are elements of some Q cohomology. So these are going to be operators that are charged under SU2R. They may or may not be charged under U1R. So some examples include the moment map related to the flavor symmetry. And so this sits in a multiplet, a so-called B hat multiplet, which contains flavor symmetry currents, and also the R symmetry current, which is related to the stress tensor. Okay, so these SU2R the SU2 highest weight states of these operators represent some non-trivial elements of a certain Q cohomology that was defined by Chris Beam and collaborators. And this Q supercharge is somewhat peculiar. It involves a linear combination of Poincaré and special supercharges. But the point is that there's an interesting set of operators that are non-trivial cohomology elements. Notice I insert them at the origin because you have this special supercharge which doesn't commute with translations. Okay, so what are some examples? So the highest weight state of this operator here is just this holomorphic moment map, the generalization of that quark bilinear that I showed you in the SU2 theory. Then there's also a raising operator, a highest weight component, let's say, of this SU2R current. So why are these guys interesting? They're interesting because they contain a lot of data that's complementary to the n=2 chiral ring. Moreover, they contribute to a nice, simple, but still very interesting limit of the index called the Schur index. So this is an index which is some weighted sum by -1 to the f over the Hilbert space with some fugacity q that's weighted by the scaling dimension in 4D minus the SU2R weight r, and it can be decorated by various flavor fugacities. And the third interesting reason to study these operators is that they're mapped to elements of a two-dimensional chiral algebra chi that was famously described again by these authors. And this chiral algebra is a collection of operators that sit in a plane in 4 dimensions. They depend only on the z and not z bar coordinate. And they have meromorphic correlation functions. Okay? So this, of course, the way I've defined this Q cohomology is just at a point, but the very beautiful insight of these authors was that by considering twists with SU2R, you can extend this cohomology construction to the entire plane and study non-trivial elements of this twisted cohomology. Okay? So I'm not going to give you the technical details of that because I don't have the time, but we're going to use some aspects of this very nice work. So in particular, when you start from some 4-dimensional theory, you have an SU2R current that gets mapped by this map chi, I'll call it the map from 4 dimensions to 2 dimensions, to some holomorphic stress tensor T. These holomorphic moment maps I mentioned in 4 dimensions get mapped to affine Katz-Moody currents. And the derivative that gets counted by the Schur index, the non-trivial Q cohomology derivative, gets mapped to a holomorphic derivative. Other derivatives take you off the plane and out of the Q cohomology. So there are also some interesting relations between 2- and 4-dimensional central charges. And you'll see these are universal relations. And of course, these 2-dimensional theories turn out to be non-unitary. But as these people have emphasized, it's non-unitary in an interesting way. It must somehow know about the 4-dimensional unitarity. So also the scaling dimension in 2D is given by this sum, this difference of the scaling dimension in 4D and the SU2R weight. Also, therefore, the torus partition sum of this 2-dimensional theory is simply given by the Schur index. So this partition sum is weighted by the usual fugacity to the L0 times some fugacity that corresponds to rotations in the plane orthogonal to the chiral algebra. And again, this can be decorated by various additional fugacities. So more generally, there are various non-trivial elements of Q cohomology that can be contained in all these multiplets. So these contain generalizations of moment maps, generalizations of stress tensors, etc. And all these states are mapped to states in the chiral algebra. So this is very complicated, and generally understanding this map is still an open question. But it's natural to first focus on the chiral algebra generators. So in other words, the operators in 2 dimensions whose sums of products and derivatives span the chiral algebra. So in the SU2 super QCD example I mentioned before, that chiral algebra is just the SO8 affine Katz-Moody algebra at level -2, and the generators are just the 28 affine Katz-Moody currents. So one very natural and very elementary question is to ask if there are some bounds on the number of generators. So I'll denote the bound as this norm of chi. Of course, the chiral algebra is infinite dimensional, it has an infinite dimensional symmetry, but I'm just asking about the generators. So it's pretty easy to convince yourself that in general there are no upper bounds. So if you can consider both isolated and non-isolated theories. So if you take SUN with nf equals to n and n to infinity, you'll see that you have an infinite flavor symmetry, therefore an infinite affine Katz-Moody symmetry in 2 dimensions, and you won't have an interesting bound, an upper bound. Also, in general, there's no interesting lower bound. You can just consider this class of Argyris-Douglas theories. And some very beautiful work by Clay and Husheng showed that these guys have chiral algebras that are just Virasoro. So in other words, their dimension, they're just generated by the stress tensor. So the claim of this talk, the technical claim, is that if you consider an interacting n equals 2 theory, and you assume that the marginal deformation corresponds to a gauge coupling, then the size of the number of generators of this chiral algebra will be at least 3. So why do we care? So arguing in favor of this assertion will touch on many of the questions that I mentioned before. So what are we going to do? We're going to consider the following general setup. We'll consider some general isolated superconformal field theory T that has a single stress tensor, and it has some flavor symmetry group GT, of which we gauge some H subgroup. Okay? And we'll make no other assumptions except that this isolated theory has a single stress tensor. And we'll want to study what happens. So the question is, what are the conditions under which this is a conformal gauging? In other words, what are the conditions under which we get a whole manifold of theories? So what are we going to do? We're going to study essentially the coupling of some H gauge fields phi to some holomorphic moment map for the H global symmetry in the theory T. And what it turns out is that it's sufficient to perturbatively and non-perturbatively keep track of operators of this type, things involving gauginos, moment maps, and SU2R currents, and the corresponding chiral algebra operators. So there's an important subtlety, which is that this Q cohomology, and therefore the chiral algebra itself, changes as you go from infinite distance to finite distance. So when you turn on the coupling, the Q cohomology is altered. So in particular, elements that would have been parts of this Q cohomology, operators in these multiplets, pair up to form long multiplets and get renormalized. And the Q cohomology changes, and so does the chiral algebra. Okay? But we'll want to, so we'll just use this fact to find some bounds. Okay, so what's the plan? So what we'll do is we'll first show that this isolated theory T has some moduli subspace that's parameterized by vevs of the H holomorphic moment maps. Of course, this proof here is not going to be entirely airtight. It's going to involve the invocation of some lore, because getting information about moduli spaces just from abstract CFTs is difficult, but I'll state the assumptions. So from this result, we'll show that if there are fewer than 3 chiral algebra generators, then A in 4 dimensions of the gauged of this conformal theory, H gauging T, satisfies these inequalities. A is bigger than or equal to C. And from there, we'll use the asymptotic behavior of the index that counts the Q cohomology, or if you like, the vacuum partition sum of the corresponding chiral algebra, to argue that there's no essential singularity in this Q goes to 1 limit. And we'll argue that this fact implies the existence of some fermionic chiral algebra generators for this range of central charges, and hence that the theory has at least 3 generators. So what do we want to do? We want to consider the following operators O that are, so I'm going to work just in the isolated theory T initially. So I'm going to take moment maps in this theory T, these mu i's, and I'm going to construct a bilinear out of them that's flavor invariant. So if that exists as a short multiplet, it's necessarily of this type, this generalization of the moment map short multiplet. And what we want to claim initially is that these operators are necessarily non-nilpotent. So you raise this operator to any positive integer power n, it's non-vanishing in the ring of short multiplets of the isolated theory T. For the aficionados of this kind of stuff, this is in particular the Hall-Littlewood chiral ring. So we'll do a proof by contradiction. So suppose this isn't the case, then there has to be some n hat such that O to the n hat is in a long multiplet, or O n hat vanishes identically as an operator. So we can deal with both cases, but for simplicity, I'm going to just stick to the case where O to the n hat is in some kind of long multiplet. So when this is the case, Dolan and Osborne have told us what type of multiplet it has to be. It has to be, again, a guy that obeys this kind of, it's a long multiplet constructed out of all these multiplets. And these multiplets contain various would-be non-trivial Q cohomology elements. One guy sitting in this multiplet, O prime plus plus dot. One guy in this multiplet, O double prime plus dot, etc. And then B hat 2 n hat contains this operator, O to the n hat. So what's the upshot? Well, at small g, this conformal manifold still has a short stress tensor multiplet, of course. But there's also an orthogonal combination of the, so these are the Q cohomology elements in the stress tensor multiplet of the H gauge fields and the isolated theory T. And so there's, of course, an orthogonal combination. And this orthogonal combination, it's very easy to check in conformal perturbation theory, is a long multiplet. And it pairs up in this way dictated by Dolan and Osborne. So then you can define a composite operator involving n hat to the minus 1 powers of this operator O times these various operators appearing here. This is a sensible definition because basically this comes from a short multiplet at g goes to 0. But the point is that this operator O to the n hat sits in two kinds of long multiplets. One, which was a long multiplet in the isolated theory T, so that this O to the n hat necessarily has some anomalous dimension, in other words, some dimension larger than the dimension dictated by the shortening conditions at g equals 0. But this linear combination of operators in this long multiplet in the theory T and this multiplet that was short at g equals 0 but acquired some anomalous dimension for g non-zero has to be short for g non-zero. But this is a contradiction because this anomalous dimension is necessarily going to 0 as g goes to 0. So what we have is that in this Hall-Littlewood chiral ring of the isolated theory T, this O to the n is non-zero for all n, and therefore this holomorphic moment map is non-vanishing as well. So this is this algebraic condition on the matter sector. This is a necessary algebraic condition on the matter sector for beta to be, in order to be able to gauge things conformally. So we can formulate a geometrical condition by just invoking the usual fact that if you have some non-nilpotent chiral operator, then you expect that there's a SUSY moduli space parameterized by its vevs. And you expect that for generic points, so this moduli space I call M0, it sits in some larger moduli space M SU2R, where SU2R is spontaneously broken, but U1R is not. And you expect that for generic points on this moduli space, it's free. So you have Goldstone bosons for broken SU2R and possible other stuff. But U1R is preserved, and so you can do a computation, Tooft anomaly matching computation, and find out what A minus C is equal to. So it's given by this dimension of this moduli space. So now you can add gauge fields and show that either A of the full theory, so this is A, by the way, of the isolated theory. You can now add gauge fields and show that either A of the 4D theory, of the gauge theory, is bigger than or equal to C, or chi is greater than or equal to 3. Because basically otherwise there would still be some kind of non-trivial moduli space parameterized by vevs of operators of this type. And the fact that it's hyperkähler, or rather that it, maybe more precisely that it has even complex dimension, necessarily tells you that you have more than 3 chiral algebra generators, because these generators of Higgs branches always map to generators of chiral algebras. So to argue that this algebra has at least 3 generators even for A bigger than or equal to C, we'll need to make an assumption that's been proven in many cases by Zohar and his collaborator Di Pietro, and also we've checked in many, many examples. And what it turns out to be the case is that if you take this beta, so if the index is the same as this twisted partition function S3 times S1, so if beta is the radius of the S1 in some units, and you take beta to 1, then this partition sum is dominated by, the log of this partition sum is dominated in this way by A minus C. So it's then easy to rule out the case of a single generator. This is just some Virasoro algebra. So if there aren't, so if you just have a single generator, it must be Virasoro. And if there aren't any null vectors, the Virasoro vacuum module is just trivially this plothistic exponential, which clearly has an essential singularity. So in other words, we don't expect that A can be bigger than or equal to C. A has to be less than C. And so what we need in order to try to accommodate A bigger than or equal to C 4D is we need to have some non-trivial null vectors. Now, non-trivial null vectors can be dealt with very easily. There's a nice general theory of this. You can just, of course, study the Katz determinant of the vacuum module of Virasoro, and you can use that plus modular properties of the vacuum character and unitarity in 4 dimensions to conclude that the null vector exists only if the this vacuum character behaves in this way, in a way so that it diverges, or it goes as e to the 1 over beta with this factor that's fixed in terms of integers p and p prime that appear in the classification of minimal models. And this p prime has to be bigger than or equal to 10. This follows from 4D unitarity. And so in particular, this will have an essential singularity. And so we have to add fermions. You can't add bosons to get rid of that essential singularity. You have to add fermions to get A bigger than or equal to C4D. And these fermions, of course, need to have some non-trivial norm in a conformal field theory. And so these different, the fermion and its conjugate will be 2 different Schur operators, and they'll map to 2 different chiral algebra generators. So plus the stress tensor that you have in the chiral algebra, you'll necessarily have at least 3 generators. So this tells us a few interesting things. So for example, it tells us that pure n equals to 2 superconformal field theories with A bigger than or equal to C need to have, just like n greater than 2 superconformal field theories, additional chiral algebra generators that are fermionic. So in the case of the further extended supersymmetry theories, those are additional supersymmetries in 2 dimensions. In the case of the generic n equals 2 theories satisfying this criterion, these are just additional fermionic generators. So, and this also gives a way to get a handle on the question of whether or not you can have theories that have non-gauge coupling marginal deformations. Because if you hand me an index or a chiral algebra that has fewer than 3 generators and a marginal deformation, I'll tell you that it's exotic, that there are no gauge fields, free gauge fields emerging anywhere on the conformal manifold. Okay, so this begs the question if we can saturate these bounds. Interestingly, the answer turns out to be yes, although saturating these bounds can't be done by a Lagrangian theory. Roughly speaking, that's because you have too much flavor symmetry, or maybe more precisely, that you get too large of a Hall-Littlewood ring. Basically, in a Lagrangian theory, when you try to get rid of flavor symmetry, you correspondingly introduce more Q cohomology elements that are not really directly related to flavor, but are related instead to additional elements of the Hall-Littlewood ring. And therefore, by a theorem that Beam and collaborators have proven, to additional generators in the algebra. So one way to get this, to get something that saturates these bounds, is to take a diagonal combination of 3 A3 Argyros-Douglas theories and gauge and SU2. And you can use some recent progress in the Schur index literature due to myself and Takahiro, and also Clay and Husheng, to show that the corresponding chiral algebra is actually the A6 theory of Fagan, and Tipunin, and it's very interesting. You can find what this algebra is. It's some algebra which is the C equals minus 24 Virasoro algebra with an additional set of 2 primaries. And you get in particular that this algebra has 3 generators, and well, you identify its nature. And another interesting point is that even though there's no flavor symmetry in 4 dimensions, you still have some sort of auxiliary bosonic algebra that acts on these operators, and that's just the action of an SL2 symmetry from rotations that are transversed to the chiral algebra plane. Okay. So the conclusion, so what have we found? So we found a bound on these chiral algebras that are related to conformal manifolds, and some new connections between conformal manifolds and moduli spaces. And we saw that n equals 2 theories with A bigger than or equal to C have to have additional fermionic chiral algebra generators. So some open questions are, it appears empirically that all chiral algebras that arise from conformal manifolds admit some non-trivial action of certain additional bosonic algebra, something beyond Virasoro. In the case of Lagrangian theories, this is affine Katz-Moody symmetry. In the case of, in our case, it was these rotations normal to the plane, which acted non-trivially on these fermions. One question is there an explanation of this phenomenon? Are there counterexamples? So again, it follows from our work, if there's an n equals 2 theory satisfying the usual scaling in the limit that q goes to 1, with fewer than 3 generators and exactly marginal deformation, then we expect that this the resulting conformal manifold is something that doesn't have free gauge fields being spat out at cusps. So, and of course, another interesting question is what additional structures are associated with chiral algebras coming from conformal manifolds in 4 dimensions. So we know that line operators, for example, play an important role in understanding S-duality, and we know, thanks to interesting work of Gaiotto, Cordova, and Shao, and also before that Hee-Chul Kim and Matt Bullimore, that extended operators in 4 dimensions and 6 dimensions have natural interpretations in 2 dimensions. So one interesting question will be to understand the role that these line operators play in the corresponding chiral algebras. And another point is that often these chiral algebras that are related to these conformal manifolds have logarithmic representations, and it would be interesting to understand if these logarithmic representations have anything to say about maybe the geometry of this chiral manifold or of this conformal manifold or something else. Okay, thank you.
You gave this argument that if a theory has a global symmetry, and it will still be in the global symmetry, then there must be a moduli space of Vauchois.
No, I didn't say that.
You said that if moment map exists.
No, I don't think it's true that every theory that has a global every n equals 2 theory that has a global symmetry has a moduli space associated with that moment. That's not true. What is true, I think, is that if you want to be able to conformally gauge that global symmetry in some way, then there is a moduli space associated with it. So if you take that theory, that isolated theory, and you couple it to some gauge fields, and that coupling is done in a marginal way, then I claim the answer is yes.
So there wasn't an argument that showed that the moment map squared is a non-trivial operator?
So the moment map squared doesn't always need to be a non-trivial operator. It needs to be a non-trivial operator in the case where you generate a conformal manifold.
Okay.
What's the theory where the moment map operator is trivial?
There are some class S examples. I don't remember the exact example, but there are many such. They've been studied in the literature in the class S constructions. So.
So what does it mean if it's trivial?
What's that?
What does it mean if it's trivial?
If it's what? Sorry.
Trivial. What does it mean if it's squared to something trivial? There's a global symmetry and you cannot gauge it.
So good. So if it squares to something trivial, and you can gauge it in, let's say, in an exactly marginal way, if that were the case, then it would imply that the theory is non-unitary.
This is a new result that you claim, right?
What?
This is a new result that you claim.
No, no. So actually, the question of if something squares to 0, let's say in the ring of short multiplets, and you can gauge it in a conformal way, the fact that that's non-unitary really follows from the work of Leonardo. You can take a formula that they find, and you can simply insert what it means for this gauging to be exactly marginal, and you can conclude then that C in 4D is negative.
What do you think becomes marginal about any decoupled sector? So imagine it does not contribute enough to beta function with any decoupled sector, trivial decoupled sector.
Mm-hmm. What do you mean by trivial decoupled sector?
So free fields. So take your interesting conformal field. Your interesting field theory, you have free fields that are decoupled. You can gauge it now.
Yeah.
In a marginal way.
Yeah, so in that case you have 2 stress tensors at least, let's say, and the story is a little bit more complicated. You still find somewhere a moduli space, but I don't guarantee that there's such a moduli space associated with each factor. So for example, you know just that the free field itself has such a moduli space, right? So clearly that statement I just made is correct, right?
So for your model, we found another realization, which is the double algebra.
Which one? Sorry.
The model you have.
Yes.
So we found the chiral algebra, which is a double algebra of D4 or something.
Okay.
So which is there's no fermionic generator.
Okay. Yeah. So I don't know. I need to see the example. So yeah, so I mean, we have this. At least we have this realization which matches the Schur index, and it has fermionic generators. So.
Thanks, Matthew again.